using Macquarie to model a structure called as beam. So hopefully you have already obtained your project assignment that was given, I think, yesterday. So you can start to form your group and do that using Finite Element software. So please choose the project because they are only given 4 or 5 projects. So ensure that you have a different project inside one group. Okay, so I will share my PowerPoint slides. Okay, this is our topic today. Our topic is to use finite element software to solve civil engineering problem. And I'm sure that last week I have given you 2 videos on how to model truss by using Macquarie. So today we want to use the same software to solve beam structure. And I will use 2 approaches. And I will leave only one approach to you, which is the line element. And I want to use the 2-dimensional beam using Macquarie in this week. Okay, so this is the lesson outcome. We want to model the given beam 2-dimensional element by using not LUSAS, but by using Macquarie software. Okay, and you have to use proper element types. Because in this beam we have to use proper element types because we have a quadrilateral element and triangular element that you can choose from, and determine how many meshing number that you should use to create such a beam model. And after that you have to assign the member section, especially the thickness, okay, the thickness of the member and also the length. Assign the given static loadings and also the boundary conditions. And after that, we have to run the static analysis by using Macquarie solver. And we can view and study what is the deformed shape or the displaced shape of the structure. Soon after that, we can get what is the stresses, especially inside your beam. You need to know what is the stresses distribution along the beam, so that you can see what is the critical part that you have to perform further analysis. So, as I said before, truss element we have studied last week, where I gave you 2 videos that you have studied on your own. And today we want to know about how to perform beam element analysis by using Macquarie. So before we have perform to use beam element, we have to know when we want to use beam element in our analysis or in our project. So if you see that in your problem, the length of that element is much more greater than the width of the depth, then that will be the indication that you need to use beam element. So let's say you have a structure like this. Oh, sorry. Let's say you have a structure like this. So I do not know why my pen cannot use. Okay, let's say I have a beam with this such small cross section, and this is the length of that structure. Okay, so if you found that the length, which is defined from this to this, is more than the width, okay, the width and also the depth, then that is one indication that you need to use beam element. So you can find this a lot in your column element and beam, where you have to use this beam element. So what is meant by beam element? Beam element meaning that all of the freedoms that is located at the ends of the elements. So let's say this is my beam element. We have nodes. We have nodes here and here. So nodes number 1 and nodes number 2 can only displace in this direction and also able to rotate in these directions. So each of degrees of freedom, we have 2 freedom where it can translate in this direction and rotate in this direction. So that is meant by beam element. And if you have a constant cross-section properties, meaning that from nodes number 1 to nodes number 2, you have constant cross-sectional properties, then you may need this beam element. And if the element can transfer moment, because the nodes at ends can rotate, so you can use beam element, and also can handle load distributed across its length. So if let's say you have UDL, point loads and so on acting on the beam, then you can use this beam element to handle that situation. So that's how you can use your beam element as compared to truss element. Truss element, the member cannot transfer bending moment. Remember last week, you cannot use truss to transfer bending moment, and that's why you have to use only truss element in last week problem. Okay, for beam, we have two approaches to model. The first approach that you can use as you did last week, you can use line element. You can use line element, or you can approximate it by using plane stress element. Plane stress element. So if you want to know what is the plane stress element, please refer to any textbooks. What is meant by plane stress element? So for line element, I don't want to do any analysis on this line element because you have done it in your two previous week where we did on bar element. Remember our bar element that you have tapered bar. Our first finite element, we have a tapered bar. So I'm using bar line element to model this. And last week we have studied also about truss element where you use also line element. So I don't want to cover this anymore because we have covered it last 2 weeks. But I want to approximate the beam behavior by this approximation called as plane stress. Okay. So this is have done last week and also another previous week where you can model the structure by using line element. Now today I want to use another kind of element called as two-dimensional beam element that we call also plane stress. Plane stress. Okay, in plane stress, you will represent that beam by using either 3 or 4 nodes. If you see on the PowerPoint, you represent the beam element by using 3 or 4 nodes element. So let's say if I have a beam, okay, maybe I will talk this later in our examples, where each of the beam will have 3 or 4 nodes element, where each of the nodes will have 2 degrees of freedom only, where it can translate either in Y or Z directions. And that will be, you can see that if you model it in YZ plane. If you model the beam in YZ plane, then each of the degrees of freedom can translate only in either Y or Z transition. But no rotation is allowed. These are used for plane stress or plane strain. As I said before, we are using only plane stress. So the common application of this, if you have a very long structures with constant cross section, such as dams, long beams, and so on. And plane stress implies that there is no stress acting normal to the cross section defined. So meaning that if I have a beam that is modeled by plane stress, okay, I can only apply the load in plane, in the plane of that axis. Okay? So let's say this is my y-axis, let's say, and this is my z-axis. So I can only apply the load in only y and z plane. but there is no load acting in x-axis. That is acting perpendicular. This is not allowed. So that is meant by no stress, normal to the cross section. Okay, so you cannot apply the stress acting normal to the cross section. That is the limitation of plane stress. And this is the types of element that, as I said before. If you see, this is, you have 3 or 4 nodes. So each of the beam element can be defined by using either 3 nodes, okay, 3 nodes or 4 nodes. Okay, so the 3 nodes in the first picture here, we can see, you can call that as a 3 nodes triangular element. Okay, and if you are using 4 nodes, you can call that as 4 nodes rectangular element. So some authors call this as quadrilateral. Quadrilateral. Quad meaning 4. Quadrilateral. Quadrilateral. So I'm sorry because my pen does not work today. I do not know why. So I have to write by using pen in the PowerPoint. Okay, these elements, these 3 nodes element, can be make more advanced if you put another mid-side nodes in between of the previous nodes, making 6 nodes. Similarly, you can also introduce interior nodes so that you can convert the 4 nodes rectangular element to 8 nodes rectangular elements. So why we have to introduce a mid-side nodes in triangular and rectangular? So I will tell you after this on the next slides. Okay, so why we use 3 nodes and triangular element? Okay, so if let's say you want to have a very just only a simple analysis, and you do not need any a lot of accuracy in terms of solution, then you can use these 3 nodes elements. So why we use this? Because we will use only fewer elements, and the effect is that you have less accurate results. So this is good if you want to do a preliminary results. If you want to, if you have get a project and then you want to perform preliminary results, so it is better you use 3 nodes triangular element. And by using this, the issue is that you have a problem with the stiffness, because you cannot represent the actual stiffness of that beam. But it has one advantage, because the analysis will be simple enough, because you will use only fewer elements, and the analysis can be run very quickly. Only the result is less accurate. So that is when you need to use 3 nodes triangular elements. How about 6 node triangular element? As I shown before, this is the 6 node triangular element. This is the second order or the quadratic version of the 3 triangular elements. If you see that, the first version here is a linear element because you have only 2 nodes. So the behavior or the displacement is assumed to be linearly varied. But if you use 6 nodes triangle element, then you assume that the displacement will be in the quadratic. Not like this, it is only in linear fashion. So using 6 node is much more better, because you will get a better solution of your results. And the problem is that by using these 6 triangle element, the computational time will be more than the 3 noded element, because you have extra mid-side nodes in between of the previous nodes in the 3 noded element. So, but the result is much more better than the 3 triangular element. Okay, 4 nodes triangular element or quadrilateral element. This is the picture. Okay, 4. And this is also give you a more accurate stiffness compared to the 3-node triangular element. And usually I will use this because it is giving you much more better solution than the 3-noded triangular element. There are also another version called as 8-noded triangular element, and this is much more better than this 4-node rectangular element because you can because you assume that the the displacement varying by second order or by quadratic equations. So by using this, the interpolation between the nodes will be much more accurate, will be increased. However, it will require more computational power and also a bit time compared to the 4 nodes rectangular elements and also 3-noded element. But it will give you a better solution. Only the time will be increased and you have to require a much more better computer RAM. However, I think by using the current software now, you cannot notice the difference time between these nodes, this element and the other nodes, because we have a much more better computer now. So the difference of time by using this element and this element is not so significant because it's very, very small. Okay, is there any questions? Is there any question from the floor?
For now, tak ada, sir.
No, sir.
Okay, to view what is the application of this, I'll give you a fixed beam. Okay, a fixed beam with the rectangular sections. The cross section is 150 by 300, so it's a rectangular sections 150 millimeter by 300. And the length of the beam is quite long, 1 meter. Okay, carries 4 kilonewton point loads here. You are required to model this beam by using line element and 2D beam element. So for line element, I assume that I have done it last week, and you can repeat to this beam. But this week, I want to use 2D beam element to estimate what is the maximum bending stress and also what is the maximum deflections. And the second question after this, how about if the beam have hollow sections with the dimension of 200 by 100 millimeter at the middle of section? Okay, so the first analysis is without the hole. The second analysis if you have a hole. So what is meant by hole? Meaning that at the middle of this beam, you have a hole with the dimension of 200 by 100. So the depth of the hole is 100 and it is situated at the middle, at the middle of the section. So that is the second analysis that we want to do, and we want to know what is the maximum bending stress and maximum deflection. So I think if you use your static knowledge and also your structural analysis, the first analysis can be done very easily. You can prove by using your theoretical mechanics to get your maximum stress and maximum deflection. However, the second questions, you cannot use your simple mechanics that you can find from your solid mechanics and your structural analysis to get this maximum bending stress and maximum deflection, because the introduction of this hole, and you need finite element software to do that. So first of all, we have to perform this by using MacWay. So for node-wise, you can refer to these nodes. So I don't want to go through to this node. You can read this node on your own, but I will give you the demonstration straight away in front of you. And these notes given to you as a guidance only. Okay, so I will open my macWay. Okay, I'm using now the latest macWay. Previously, I'm using macWay 12. So now I'm using macWay 13. So last week, why I cannot do the online presentation, because my computer has been formatted, because I have problem with the boot sector. So that's why you can see that my screen now is almost clear. There are a lot of files, but because all the files have been deleted. So that's why last week I cannot do any lectures because my computer was formatted. And that's why I give you the videos only. Okay, so I will open my macWay. Is it my macWay already open? Okay, I will open my macWay. Okay, for starting your analysis, if you point your mouse here at the top, you have analysis static 3D. And as I said before, you have to use plane stress. So what is the meaning of plane? Plane meaning that you have to use two-dimensional analysis only. So you have to double-click this analysis, click to the static 2D, okay? Ensure you click to static 2D, and change the solver here from internal to CCX. Okay? From internal to CCX, because you want to make use of the solver, the advanced solver here. So click OK. Okay? And now you are ready. Okay, what you should do after this, we have to define the nodes of the beam. To define the nodes. So if I put my dots here, so I have to define the 4 nodes that making our beam here. Where my first nodes here, this is my nodes number. This is my nodes number 1. This is my nodes number 2, nodes number 3, and nodes number 4. And if I assume that this node is 0, 0, so for sure this node will be 1, 0. This third node will be 1, 0.3, because the depth of the beam is 300 millimeter. And the nodes of the 4 points will be 0, 0.3. So that will be created. So by clicking these new nodes, and I'll create my first node here. My second nodes will be 1 meter. Okay, you may see that my first node here. And you can see that the coordinate here, if I point my node, is 1, 0. And my third node is 0.3. Okay, this is my third node. And my final node is 0.3. Okay, so I will click close. And I will zoom to window. Okay, so you can see that points. If you want to see the nodes number, you can click this show nodes number. Okay, and if I want to see in my XY plane, you can view that in XY plane. Okay, now click this new element. Okay, and as I said, on 2D, you have to select 2D. You have this 3 noded element, 4 noded element, 6 noded triangular element, and 8 noded rectangular element. So I want to use this quadrilateral element, 4 nodes, and I will connect that. Okay, you may see that the nodes, the element is created. The element number is created. Okay, so it's better I save the file. Okay, so now I want to, I have already select the element, which is the quadrilateral element with 4 nodes. And then I want to define how many mesh for this element. So I have to select this face, select this face icon, where you can select this face. right click your mouse, click under mesh tools, click under refine, and click under custom. Okay, now we have options here. We are using now quadrilateral, so I have to define my vertical meshing R and my horizontal meshing S. So this is the number of meshing in my vertical. So let's say I will mesh it into 5 divisions in the vertical and 10 division in horizontal, and T will be the for the 3-dimensional element. So you are not using 3-dimensional element here. We are using 2D, which is quad. So click apply. So see carefully when I click apply, you may see that the vertical direction will be divided into 5 equal divisions, and my horizontal will be divided into 10 equal divisions. Click apply, and you can see that it is already divided. So this is that we call as meshing or discretization. So because our free version here is only limited to 1000 nodes, just to check only, mesh tools under nodes element list, check the number of nodes. Is it more than 1000? It is okay. So we are in the our limitation. We can use the software. So in this case, we have to work within the given nodes only, because the maximum node allowed by this free software is 1000. Okay. So now we have already done the meshing and also element selection type. Okay, now we have to define what is the section properties of this, and also the material properties. Where is it? Oh, okay. So the section properties is 150 by 300 millimeter. The width is 150, but the height is 300, and the Young models is 200 gigapascal, right? Okay, so just click this. So when you click this 50 element, it will be straight away click on the whole element. Right click the mouse, assign new materials. Just click this shell and membrane, and you have to define what is the thickness. So what is meant by thickness here? Sorry, I think I have to close this. The thickness is what is the thickness in the Z direction. If you still remember, this is your X and Y. This is your X and Y. So I want to know the Z direction thickness. The thickness towards to your face. So the thickness toward your face is 150 millimeter. So I have to select this again, assign new material, and this is millimeter 150. So we are not using any plane strain, we are using only plane stress, so do not check this. Okay, click the mechanical, isotropic, change this to be gigapascal, and this is 200 gigapascal. Click OK, and you may see that the red color of the 50 element has been gone, because you have already assigned the what you call that, the material properties and also the section properties. Okay, remember that in our structure here we have fixed here, and remember in 2D, and when you use plane stress, you only can fix only the translational on part, but cannot constrain the rotational parts. So what you should do now, I will select this nodes element, where I can select these nodes, so that I want to assign the fixicity there. Right click here, load and constraint, right click, new displacement. So I want to constrain my displacement in X. So I just click this X and make it the displacement to be 0, because there is no displacement in X. Click OK, and you may see that our structure has been constrained, cannot be moved in X direction. Right click again this, new displacement, click Y, and we see that that Y is activated, the rest is inactive, is constrained to be 0 there. Okay, and you cannot perform any rotational constraint here because it is is a plane stress. So that is our assumption here in plane stress. And for the the loads acting at these nodes, which is 4 kilonewtons. So I will select that nodes. Load and constraint, new force. This is in kilonewton, acting in Y by -4. So I will click OK, and I will save this, and we are ready for the analysis. So how to perform analysis? Very easy. You just click this, and the green color stating it is OK. So I can make it this smaller by zooming. You can scroll your mouse using the third rolling button. Okay, you can zoom in and out. So if I click Y, so Y here meaning that the displacement in Y direction, you may see that it is 0 displacement meter here is correct because this part cannot be moved, but it is gradually increases the displacement until to the blue color here, where the displacement is about 1.722 10 to the power of -5 meter. So if you want to see the displacement, this is the displacement form, the deformed shape. And if you click this, this is the undeformed shape. And if I click this, you can see the animation showing how the beam is deflecting when you load and unload the beam. Stop the animation if you don't want. Okay. And if you want to have this picture, you can click this edit. You can copy this image, click copy, and you can open your words. So let's say I'm creating a new words document, and I will paste it, and you can have the picture, and you can put your figure name and so on in your project. Okay, so remember this answer is only valid for 5 division, 10 division times 5. So maybe you have to perform the mesh study or mesh conversion study using another scheme of meshing. So maybe you can increase the meshing by 20 by 5 and see what is the result of the displacement, and repeat the same exercise until you see the maximum displacement is almost constant. And when the answer is almost constant, you can see that it is already converged to the correct solution. So that is the displacement. How about the stress? So you can click on this button, stress, and we want to get the stress in XX direction. So you can see that this is the stress in XX direction distribution, where you can see that the stresses is varying from the negative here, negative Pascal. So I think I want to change this to be megapascal. So from the bottom here, we have a compression stress, which is about 1.3 megapascal, and varying gradually to be somewhere here to be 0. So 0 may be between the color of this light green and dark green. So somewhere here will be a 0 megapascal, and after that it will be increased back to the tensile stress is about 1.3. So if you want to view this in 3-dimensional, I can click this isometric view. Okay, and if I want to view the thickness, I can click this show thickness, and you can see that the thickness of from here to here to be 150 lah. And I can rotate. I can rotate to view and study where is the location and the stress distribution inside the beam. You may see that the stresses is varying from compression at the bottom here to tensile stress at the bottom. Because remember, this is a beam, you will generate tensile and compression on the maximum fiber, whether the bottom fiber or the top fiber. Okay. So if you want to see the displacement, you can view the displacement in 3D. Even you can rotate this, you can study. So far, is there any questions? Is there any questions?
No, sir.
Okay. So if you like that picture shown here, you can go to the edit and copy image, and you can open any document, Word or what, doesn't matter. You can paste. Okay. And if they say you want the 3D, you can click this 3D, and you can edit and copy image. And also you can paste, sorry. And you can put in your report for your project. But remember, you have to perform convergence study, because this is not the correct answer for it, because you have to perform the meshing mesh convergence study. Okay, the next question asking you, how about if we have hollow? Right? We have hollow section. Okay, it's the same thing. So I will click new, and I don't want to save this. So we have to create the same. So I will open back my example. Okay, example, and maybe I want to. I think it's better I using another file. Okay, so I will create our structure. So this is 0.3. This is 0. Okay, click close, and then I want to zoom it. So I have to create the hole somewhere there. So the hole there the coordinates will be, because this is 200 by 100. So 200 by 100. So if you calculate, so we have to perform some calculations here. Oh, sorry. In actual, I want to create shapes only. Okay. So the coordinates here will be 0, 0. Okay. This will be 0, 0. The coordinates here will be 1, 0. But the size of the hole is berapa tadi? 200 by 100. So the size is 200 by 100. Sorry, my arrow is not straight, but this is 200, and the height is 100. Sorry, 100. Okay, so I have to know what is the coordinates here. Okay? I have to know what is the coordinate of the hole. So I have to create the dots here. So what is this coordinate? I have to know. Okay, that coordinates I have to know, because I want to create in my Macway these nodes, and also these nodes. So we have already created the 4 nodes, 1, 2, 3, 4, but the inside node we have to determine. So can you help me to determine what is the nodes of my first point here? Berapa ni? Situated at the middle. So meaning that the distance, sorry. this line will be 0.5 lah. From here to here is 0.5. This is 0.5. Okay. And also this line should be black in color. Okay. Must be in middle. That distance is 150 lah. Or 0.15 lah. Oh, sorry. So can you help me to find what is my nodes coordinates here? Boleh tak salah seorang? Berapa situ? Berapa koordinat tu? Are you with me? Atau semua dah tidur ke ni?
0.4.
0.4. Kemudian?
0.05.
Okay, how about the second one? That will be 0.6 lah kan? 0.05, isn't it?
Yes.
Okay, the third one kat sini. What is that coordinates? That will be 0.6. Kemudian 0.15, isn't it? Pasti ke? Yang 0.05 ni saya pelik sikit Macam ada tak betul sikit. Yang ni 0.4, 0.15. Betul ke 0.05 ni? Cuba check betul.
0.1. 0.1.
Yang bawah ni? 0.1 kan? Saya pelik sikit. Sini 0.1 Yang ini maksudnya akan jadi 0.2 lah, isn't it? These are 4 coordinates we have to input. Again, tengok balik tadi 0.4, 0.1, 0.4, 0.1. Click add, see. Yeah, it is added there. 0.4, 0.1. And then after that 0.6, 0.1. Okay, and then 0.6, 0.2. And the last one is 0.4, 0.2. Okay, so I will click in this plane. Okay, see what is the nodes number. Okay, so now we want to create the surface. Select quad. So I will select this, 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 and this. Okay. Select this, 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 and this. Select this, 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 and this one. Okay. So can you see that the difference of doing the previous example and now is a bit different? Okay. So we have already select the element types, which is quad 4. Okay. So if you want to use another element, let's say quad 8, it permissible. Doesn't matter. You can try on your own after this. Try also can. Triangular 6 also can. But I like to use this because much more better than try. But quad 8 is much more better than quad 4. The only reason that I want to use quad 4 because of the nodes limitation to be 1000. So that's why I'm using quad 4. Okay. Again, what you should do, you have to select this. Okay. Select one of the face. Right click your mouse and mesh tools, refine, custom. Okay. So I want to know, I have to establish what is my division in row, let's say to be 4, and for my horizontal, let's say to be 5, let's say. Click apply, okay. So repeat the same thing. Okay. Okay. So just check the number of the nodes. Cannot be more 1000. Okay. Still okay. For actual in your work, you don't have to check this number of nodes because in our class here it is free version. So please take note, jangan buat benda ni masa kerja. Tak perlulah check sebab sekarang kita gunakan free version, dia limited. Okay, again we have to specify the material properties again. The thickness is 0.15 or 150 millimeter. It's the same. This is also similar, 200. Okay, and as usual, select these nodes, and you can define the new displacement. Okay, do the same thing. Displacement in Y. Okay, and this is the loads. A new force in kilonewton, which is in 4. Okay. So let's say I save this as hollow. Example with hollow. Okay, and I didn't remember this, but never mind. Just click this static 2D, CCX. So no problem, you can specify it later and run it. Okay, green meaning okay, and you can see now the displacement is a bit different. It's a bit different. If you compare with the previous one, there is no change of displacement like this. Okay, but here displacement also a bit different because previously it's about 1.7 something, but now the displacement is 1.78. A bit different. So if you want to see the deflection, this is the deflection, and this is the animation. Okay, the animation. And if you want to see the stresses in X, can you see that it's a bit different from previous? If I see in thickness, it's very different from the previous. So you can study which part. So you can see that there is a stress concentration here. There is a stress concentration here. So if you zoom, then you can see that the stresses is about 8.4. So maybe the unit is megapascal here. So Pascal here, maybe I want to change to megapascal, and I can zoom to see what is the stresses here is about 0.8 here. So you need to do something here because you have a lot of stresses here in the hole. So maybe you can put extra reinforcement here in your design to combat these extra stresses. So you can see that you can analyze a lot of things here just by using software. You don't have to perform any calculation manually. So here you need extra force, reinforcement. If let's say this is made from concrete, logic lah, because tempat ni ada moment. Sekejap, saya betulkan balik kepada keadaan asal. Saya kecilkan sedikit. So logic lah, tempat ni memang fix. So you should put extra reinforcement because the stresses is about 1.083 mega. Mega maksudnya kali 10 kuasa 6 is quite large. And also we have tensile stress here, compression here. This is tension. Sebab dia because this is a cantilever. Cantilever, you must have tension at the top, compression at the bottom lah. But here the stresses is not so big in bending because it's almost 0.019, but you still need to put extra reinforcement but not so much as here. But at this place, tempat yang ada lubang ni, nampak ni, you need reinforcement here. You need reinforcement here extra here because you have extra stresses here. Bukan hijau, hijau agak 0 tapi sini bukan hijau. Dia ada something yang dekat-dekat merah ni, 0.8. So at this place you have to put extra reinforcement. So this is how you can use finite element software to guide you to perform design. So I don't need to do any structural analysis. I don't have to use any slope deflection and so on because this problem saya tak boleh gunakan pun slope deflection, moment distribution. I need software because we have hole there. So can you give me example where you can have hole inside your beams? Ada tak siapa-siapa sini tahu di mana kita ada hole dalam beam? Where you can apply hole inside your beam? Di mana? Ada tak siapa-siapa ada idea? Any idea? Senyap aja semua ni. Halo? Ya Azim?
Tak sure.
Tak sure. Ya Allah, orang ni dah semester berapa ni? Tak pernah tengok beam yang ada lubang kat tengah-tengah? Tak pernah? Tengok beam semua padu je, tak ada lubang Sometimes you have to allow conduits of electricity punya line ataupun piping. Pipes kena masuk dalam beam. So you have to design a beam where you have to put holes supaya pipe-pipe ni ataupun conduit elektrik boleh masuk. So that's why you have to introduce holes. So in order to design beam with holes, you tak pernah belajar pun dalam CES 522 pun. How even also in your structural analysis you tak pernah belajar pun how to find stresses in holes, tak pernah. So you have to use finite element software to guide you or to help you to get what is the stresses there so that you can put appropriate amount of reinforcement to combat the stresses developed inside the hole. Faham tak? Okay? Boleh? Okay. So I think that's all for now because I have already conveyed this part. So please do your you punya project by groups and submit it with within the required time. So ada apa-apa tak sebelum saya berakhir? Ada apa-apa? Dan ingat you punya practical test akan dilakukan pada 10 hari bulan 1 pukul 9 pagi. Tolong nanti sama ada buka Google Classroom ataupun email yang you gunakan untuk register GC sebab dalam email tu nanti you akan dapat soalan. Tetapi bukan sekarang lah, pada masa kejadian. You akan dapat soalan masa itu. Pastikan semasa itu, masa you nak hantar nanti, video you mengandungi screen record of your code. Maksudnya saya nak tengok macam ni you buat tu by video and your face must be recorded within 20 minutes. Tolong semasa submit video tu, submit video file dan juga submit dokumen yang dapat email tu dengan you tulis nama you semua dan hantar juga declaration form tolong juga sign dan hantar serentak sekali. So maksudnya akan ada dua file submit lah. Satu file video bersama sekali dengan file yang PDF yang you tulis nama dan sign semualah termasuk sekali declaration form. Okey, jelas
Jelas.
Okey, so kalau jelas,
Yes, sir.
kalau tak ada apa-apa soalan, saya akhiri kita punya kelas lah. Okey, thank you all dan jangan lupa you punya attendance pukul 10 kena sign dekat apa ni you future macam biasa. Okay, that's all. Assalamualaikum warahmatullahi wabarakatuh and very good morning.
Thank you, sir.
Thank you, sir.
Thank you, sir.